Hi everyone and welcome to this video on Machine Learning Mastery course, and in this video we're talking about regularized linear models, which is elastic net regression and lasso regression. This is elastic net and lasso regression we'll talk about. As I will spend about 5 to 10 minutes for this video because it's only about equations and understanding, because you have already seen the video of linear regression and ridge regression, and I hope that you got familiar with both of. So I have not to tell about why we use regularization. The one and only reason for using regularization is it prevents an overfitting, okay, or fitting the nonlinear model. Okay, so let's finish this video in a fast way. So what is a lasso regression? It is also called the least absolute shrinkage and selection operator regression, a very long name, so that's why this is called lasso in short. Okay, lasso regression is just like a ridge regression. So what in ridge regression we are doing is that, let me take a black. Okay, so what in ridge regression we are doing, we are taking the L2 norm, where W is the containing all the parameter vector, means theta 1, theta 2, theta 3, all the way down to the theta n. Okay, so this W contain it is a feature vector, feature weights vector. So we are taking out the L2 norm, but in case of lasso regression it is taking out the L1 norm. So what is L1 norm? So you can see here that the L1 norm looks like this. We are just adding the absolute value of theta I, and again we have to accept theta 0, okay, and we have to do explicitly for theta 0, and we have to do this the absolute value of theta I all the way down to theta I. Okay, so this is what a simple lasso regression is. So let's talk about the difference between lasso and ridge regression. So what is the difference between lasso and ridge regression is, ridge regression means, why we use regularization? It is simply because it makes the feature weights, means thetas to closer and closer to zero, So ridge very lessly remove the feature close to 0, or the lasso regression makes the means remove completely. Means what I'm saying is that in ridge regression, let's take an example, theta 2, it makes closer and closer to 0, but in lasso regression, this is a ridge regression, so in lasso regression it makes completely 0. It makes closer and closer to 0, but in lasso regression it makes completely closer, means completely 0. So it means removing the features if we are saying 0. Okay, do you have understood? Okay, so this was the difference between, you can take a look at these two features, important features. Okay, so let's implement lasso regression from very scratch. So I have already written down, so it's a waste of time, so if I write here. Okay, so we are defining class lasso regression. It is the init. It is going to take the learning rate, iterations, how many iterations, and L1 penalty. And in the previous video we had talked about ridge regression, so let me open about ridge regression. And we have also talked about polynomial regression. So in that we have implement our we want L2 penalty, but in this we want L1 penalty. Okay, so we are self.learning rates. We are doing the same thing. If you need to know about the object-oriented programming, we are fitting it does all those things that are required, means gradient, descent, cost, and all those stops, and is updating the weights by taking out the cost function by dwj and dwj, means again the same thing happens, but it removes the L2 penalty with L1, okay, instead of using L1 instead of L2. And if it is very kind of disgusting, I could say. You can see this how we implement from very scratch. It's a very good idea if we implement from the scratch, so we understand how actually algorithm is working. But in real life you should use this. In real life, means for a learning purpose this is good, but in real life you should use scale learn lasso, so it provides more efficient way to do that. Okay, this is what it, and let me run this to code. Okay, run this. Okay, and this will give the output 4.69. This we are calling the predict function. And again, what we are doing, we are making the instantiating here. And if you don't know what it is, we are instantiating so that we can use this object to fit this to predict anything. Okay, so this is our object, so it is we are instantiating, and then we are fitting and predicting. Okay, so this was it for Lasso regression, and I hope that you got better intuition about Lasso. Again, the simple expression is Lasso regression is a regularized linear model which will help us to fit nonlinear data or to prevent for overfitting, and it uses L1 norm instead of a ridge in L2 norm, which is often used in ridge regression. So I will ask you for more detailed introduction on regularization to watch my previous video, which is a ridge regression and a polynomial regression. Okay, so now we'll talk about another kind of regularized linear model, which is elastic net. Elastic net is a mixture of both ridge and a lasso regression. It has a hyperparameter R. It is a mixed ratio. It is a mix, which is a mixed ratio, and if R equals to 0, then it's simply equivalent to ridge regression. If we set R equals to 0, then it's simply a ridge regression, and if we set R equals to 1, it is simply a lasso regression. So we have to tune this hyperparameter. So you may think, hey Ayush, what is hyperparameter? Just for now, we'll tell hyperparameter it means that we have to choose it by ourselves. We have to tune it. We have to choose different and see what our model does. So that's called the hyperparameter, and parameter is simply the parameter that are required. Okay, but in hyperparameter we have to tune it. Okay, means alpha is a hyperparameter. We have to understand how much we have to take the learning rate. Here R is the hyperparameter, L1 penalty is a hyperparameter, L2 penalty is a hyperparameter. So these are the hyperparameter that we have to use. Okay, pretty much easy. And again, you can see here alpha equals to 0.1. We are taking, you can take any of them. And alpha here is this alpha. You can see here this alpha, and it obviously uses L2 norm here. Okay, so the equation of elastic net is something like this. The equation of elastic net is something like this. You can take a look that this is a mixture of both ridge and lasso regression. Lasso regression. Okay, the notebook in the description box below, you can take a look at that. Okay, so again the same thing will happen. I have already demonstrated you that we now the mixture. So we want L1 L2 penalty, and then it wants of the weights, and we are just doing the same that we were doing above. So it is for understanding purpose, but I didn't recommend for using a real life. I recommend using the scikit-learn library, which is an elastic net. Okay, I think it's elastic net. Often you will ask now, hey Ayush, what is the difference between these? And I will say I will make a video upon that which regularized linear model to use. But for now, don't worry about it. Just use whatever the fit the model is. Okay. But if you want that, if you have a lot of features, so you can use lasso regression. If you have a small set of features, use ridge regression, and you can take a look at the elastic net on the internet. Okay, so that's it for this video. I'll be catching on next video, and in the next video we'll talk about this is it for all kind of linear regression and regularized linear models. And I hope that you also done a program assignment, and also from the next video we'll be starting talking about logistic regression, which is often one of the powerful classification algorithm, and we have covered everything in regression algorithms like linear regression, ridge regression, lasso regression, elastic net, and some kind of gradient descent algorithm and all those kind of stuff. Okay, so in the next video we'll be actually starting with logistic regression, and in the first we'll understand the theory, and in the next video we'll develop the logistic regression from very scratch, and that will be interesting. Okay, so that's it for this video. I'll be catching up in the next video. Till then, bye bye.